Okay, let's start. We'll get through some more examples here. Try these. Integral from 0 to 1, x of x. Integral from 0 to infinity, minus x. Integral from 1 to infinity. Okay, so in theory, nothing new to teach. We're just going to do a few examples to get comfortable, more comfortable with these guys. A, B, C, D. Okay, first one. How do we do it? Okay, 0 to 1 of x ln x dx. Maybe someone clean the board up. Ideas. What do we do? Yeah?
Use integration by parts.
Sure, but there's a setup before that. Yeah?
So it's undefined at 0, so do...
So 0 is a problem. That's the first thing you were to recognize. So it's an improper integral because there's a 0 there. Why is 0 a problem? Log of 0 is undefined. So basically we're going to think of this as the limit, let's say n approaches 0 on the right, of n up to 1 of x ln x. And so now we can worry about the integration technique that we're going to employ. So, and you said you want to do integration by parts. Okay, what would the parts be?
U equals L.
U would equal ln, right? Because remember in integration by parts, we follow that thing that says liate, and so we have an L and an A, so this guy gets to be the U. So your du is going to be 1 over x dx, and therefore your dv will automatically be x dx. And so your v would be the integral of that, which is going to be x squared over 2. And so this is going to be equal to u times v minus the integral, and this is of course going to be evaluated at n in 1, minus the integral of v du, which is going to be x over 2. Notice I'm leaving the limit there because I didn't take the limit yet. I'm worrying about computing this integral first. So that becomes x squared over 2 ln x minus integral of this
1/4 x squared.
x squared over 4 and all of that is between 1 and n. So this becomes the limit as n approaches 0 from the right. Plug in 1, now we apply the fundamental theorem of calculus. So right now the limit is just staying, we're not taking the limit yet, we're actually just worrying about the integral. Apply the fundamental theorem of calculus. If I plug in 1 into this, what do I get?
0.
0, because log of 1 is 0. So I get 1 into here, that's minus 1 over 4. Minus, plug in n, so I get n squared over 2 times ln of n. Minus, well now it becomes plus, well let me put parentheses here. Plus n squared over 4. Right, so now all the integration is gone, and so now we only have to worry about this limit. So how do we deal with that limit? Right, the limit of a sum is just the sum of the limit, so we can even think of it this way. Limit as n approaches 0 from the right of minus a quarter minus the limit as n approaches 0 from the right of n squared ln of n over 2 plus the limit as n approaches 0 from the right of n squared over 4. Okay, so these two aren't so bad. That's minus 1 over 4 because it's a constant. This guy's just going to be 0. What about the guy in the middle? What does that become?
Because n would go to infinity, but then n squared goes to 0.
So this goes to 0 times infinity. And what's that?
So you can often tell us for that, don't we?
No.
2.
But what is that called when you see something like that? Guys remember the book? It's called an indeterminate form, meaning you don't know what the answer is. It could be defined, it could not be defined. So we kind of have to do something here. What do you think we can do? Can use L'Hopital's rule, but what's the form for L'Hopital's rule? Where does L'Hopital's work?
Quotient. Or
Huh?
like a quotient.
It has to be a quotient, right? So for L'Hopital's rule to apply, you have to have the form this or that, right? It doesn't apply in otherwise, okay? So what we need to do is, we need to rewrite this to be in one of these forms. How do you think of doing that?
It's infinity over 0 plus, which would be infinity over infinity. Or
So how are we writing it?
like 1 over 0 plus would be infinity.
I'm not sure.
I don't know. I'm just thinking.
We have 0 times infinity, which means it's indeterminate. So you're thinking, okay, I also know the technique of L'Hopital's rule, which that's what I would try to apply here. But to apply L'Hopital's rule, I need to have one of these two forms. So before doing anything, I need to rewrite that in one of these two forms.
We could do like ln n over 2 over n squared. Because then the 2 over n squared part would go to infinity,
Right,
right?
bring the n squared into the denominator, now it becomes n to the minus 2. So if you, and so that becomes 1 over n squared, which we know as you approach 0 from the right of x to the minus 2, that goes to infinity, as well as you approach 0 from the right of ln, that goes to negative infinity, so that gives us the infinity over infinity form. And so now, I can apply L'Hopital's rule. This guy's going to stay here. Oh, well, there's a negative here. And so what would that become by L'Hopital's rule? This is equal to the limit as n approaches 0 from the right of
-4n to the -3.
So in other words, let's do this, minus. So in other words, I can bring the n cubed up. It's 1 over n cubed, so I can flip it and multiply the top. So I'm going to simplify before doing L'Hopital's rule, because that, if I might not need it. If I bring up the n cubed, that's going to cancel with this guy. It's going to give me an n squared on the top over -4. And what's that as you approach 0? It's just 0. So the answer ends up being -1/4. So it converges.
Do we just say for the answer that it converges and then write what it converges to?
You can say converges to -1/4, but I don't really care, right? Converges. Just make sure you say converges. Okay, so this is kind of showing you that the limit techniques, you need to still remember those guys, because they will come back. And you kind of have to be doing them while you're doing something else. So you need to be very good at them, recognizing when a technique would work or not. 0 times infinity is an indeterminate form. The main technique we know to deal with those is L'Hopital's rule, but it requires that you rewrite it in 2 specific forms. Another thing that works out a lot of the times, I think, did I tell you guys that? About the order of magnitude of functions, about how polynomials relate to logarithms. Did I ever write that down? I feel like I did. Like x to the n, it's always super bigger than ln of n, and that's always smaller than, say, a to the n, and so on and so forth.
No.
Sounds vaguely familiar. Maybe that was from SAT prep.
I feel like I kind of, but I could be wrong. Right? Like polynomials are always bigger than logarithms of the same order. In fact, even if the orders are slightly smaller. And exponentials are always bigger than logarithms. Factorials are always bigger than exponentials. And something like that is always bigger than that. So the idea is, if you, I think I mentioned this, but I don't remember. So in the idea is, if you see something like x squared over e to the x, the idea is the exponential will be so much bigger than the polynomial that it's like this guy's nothing, and you just kind of equals 0. You can say it as it's kind of like a shortcut, because exponentials move much faster than polynomials, and so this infinity is going to infinity a lot faster than that infinity, and so it's kind of like a constant over infinity, and so you get 0. So that if you understand the relationship between functions, you can actually get to the answer a lot quicker. And just by knowing, for example, that if there's a polynomial versus a log, and you're going off to infinity, the polynomial will always win. It will grow so fast that this guy would be like nothing compared to that guy when you're off to infinity. And there's a succession of these functions that kind of work like that. So if you have an exponential fighting a polynomial, the exponential is going to win. Right? If you have a factorial fighting a log, the factorial is always going to win, and so on and so forth. And so you could have, when you saw this 0 times infinity, one thing you could have also noticed is that you really have a polynomial and a log fighting each other. The thing is, the polynomials move a lot faster. So it turns out that this guy's moving to 0 a lot faster than that guy's moving to infinity. So he overwhelms that and kills it. And so you can kind of look at that and sort of know that the answer should be 0. Okay, so that's just another thing to kind of double check whether something should make sense or not.
So that order of magnitude thing just means that, like,
It tells you which functions converge faster.
Okay, okay.
And so if they're ever racing to a point, one is going to be there a lot quicker than the other guy, and that can have implications about limits.
Okay.
So we did this one. This one actually converged, even though ln of ln of 0 was undefined, but because he's battling a polynomial, the polynomial kind of controlled the integral and forced it to converge, even though the ln itself wouldn't have converged. What about this guy?
Oh, quick question.
Yes.
I may have missed this. Can you use that to justify sort of skipping L'Hopital's rule there? Say that the x just grows faster than the logarithm function? Or would you have to?
Sure, I'd accept that, but I'd rather you indicate that that's what you're thinking. I need to know what you're thinking, that it wasn't just a blind guess.
Right.
So if you like skipped from this line to this line and say because n squared moves faster than ln, or something similar to that, I would accept
Okay,
that.
cool. Just showing.
So if you're making a leap in logic, I need to know that you have the right logic backing you up, and it's not just a wild guess, or worse, a wrong guess.
Cool.
Yeah.
Thanks.
So if there's like a limit that you really don't know how to deal with, but you kind of see the functions involved, and you kind of realize, well, this guy is going to be a lot bigger than that guy, so I can kind of focus on what this guy is doing, and that kind of gives you an idea of overall what's happening, and you can just jump to a conclusion there, but you need to make sure that you kind of tell me what you were thinking.
Cool.
So you can write that phrase. You could also write something like n squared. The notation of this word kind of inequality where they do a double inequality to show that, yeah, this guy's like, you know, compared to that guy, he's the much stronger guy. Okay, this one. Yeah?
You have one, it's going to infinity at one of the ends, so you have.
Right, so it's improper because of that. Otherwise, it's okay because the exponential is always defined, e to the minus x is always defined. So really, the infinite limit is the only problem. So let n approach infinity of 0 to n of e to the minus x dx. What's the integral of e to the minus x?
Negative e to the negative x.
Minus e to the minus x, between 0 and n. Apply the fundamental theorem of calculus. Plug in the n. Minus, which becomes a plus because it cancels here, plug in the 0. And as n is approaching infinity, what happens to e to the minus n?
Approaches 0.
Goes to 0. And so this guy, e to the 0 is just 1, so that's actually 1. So it converges. C 1 to infinity. Do you have any intuition here? Do you feel like this will converge, diverge? If you were to hazard a guess, what would you guess and why? Yeah?
Diverge.
You would guess diverge? Why? What's your reasoning? See, like that's what I don't want you to do on a test.
Converge.
Why?
Because there's a negative x. It would
Okay.
just, and you play like infinity in for the negative x and the exponent, usually it goes to 0. So then,
Oh, for the, yeah, but this guy would go to negative infinity though. If you look at this function, if my x goes off to infinity, then this expression here goes off to negative infinity.
Isn't your exponential going to move a lot faster than the polynomial?
Yeah, the function that we have here, it's 1 over x divided by e to the x, right? Now if your x is going off to infinity, now both of these guys are going off to infinity, but this guy is a little infinity, well that guy's a big infinity, right? So it's like this guy is approaching 0 very fast. So even though I'm taking an infinite area, I'm not exactly sure what this function looks like, or pretend it looks like whatever. I know that as it gets larger and larger, it gets very smaller. I'm finding the area from 1 to infinity, but the guess I would make is that because the exponential is so powerful, it's approaching 0 so fast that at some point the area is going to stop growing. At some point it's going to be like I'm adding 0 area. Right? And it's kind of, I get that intuition because I have a polynomial fighting an exponential. So my guess would be that it would converge. Okay. So that kind of gives, like building a certain intuition kind of helps you expect an answer. And so if you do the problem and it doesn't sort of agree with your intuition, you can kind of know that I probably made a mistake, as long as your intuition was based on the right reasons. So I would guess that this converges, but let's just make sure, because I really have an exponential approaching 0 a lot faster than this guy's approaching infinity, and so I feel like the area is going to be like adding 0 after a while. But again, this function is always defined on the entire real line, so the only reason why this is improper is because of the infinity. So let n approach infinity from 1 up to n, 1 minus x e to the minus x dx. Okay, now how do I integrate that?
Part.
Integration by parts, what are the parts?
U is 1 minus x.
Right, liate, so that would be my u, and this would be my dv.
Could you also split it into two intervals?
Huh?
Could you have done it into interval of e to the minus x minus integral of x e to the minus x?
You could, but you like to expand the parentheses and do this.
Yeah.
You'd still need by parts though.
Yeah, so that would be my point. You could do that, but it doesn't really save anything because you still end up doing by parts here. So you might as well just do it all in one shot. But it wouldn't be wrong to do that, but I don't see the benefit in doing it in this case. I'd still end up having to do by parts anyway. So I'd say u equals 1 minus x, so my du is minus dx, my dv is e to the minus x dx, so my v is minus e to the minus x. So this is the limit as n approaches infinity of u times v minus the integral of v du. And again, this is going from 1 to n, that's going from 1 to n. So this is just x minus 1 times e to the minus x minus, this becomes a plus e to the minus x from 1 to n. And this just really simplifies to x e to the minus x. So I end up with this limit as n approaches infinity, n e to the minus n minus e to the minus 1. How do you do that limit? So that's guy just a constant. What's happening to this guy? What's going on here?
Infinity over 0.
It's infinity times, well, infinity times 0. So it's indeterminate, but I can rewrite it.
So it's n over e to the n.
Yeah, so that's the limit as n approaches infinity of n divided by e to the n. I can rewrite it as that. What's gonna happen here?
Yeah, infinity over infinity.
It's infinity over infinity, but it's gonna go to 0. Again, the exponential goes a lot faster than the numerator, which is a polynomial. And so
It's just whatever.
that's the guy. It converges. One thing you could have done is here, you would apply L'Hopital's rule. And you take the derivative of that, which is 1, divided by the derivative of that, which is still e to the n. And then that clearly goes to 0, because it's 1 over an exponential. So applying L'Hopital's rule, you could just rewrite this, differentiate the top, derivative of n is 1, differentiate the bottom, it just stays the exponential. Okay, that should show. And then this obviously goes to 0. D.
Wait, you have it written as 2 there, so. Did you make
Oh,
it?
did- Yes, I did need to.
Can't you just differentiate?
Or you have to break it up.
Hmm?
You have to break it up first.
Break it up how?
It's
Yeah.
undefined at 0, which is on the interval.
Right, it's undefined on 0.
Yeah.
So 0 is a bad point. So I have to first break it up. This is minus 1 to 0, dx over x cubed, plus 0 to 2, dx over x cubed. So it's an improper integral because 0 is a bad point. At 0, I divide by 0 because there's an x cubed in the denominator. So this is going to be equal to the limit as n approaches 0 of minus 1 to n, so x to the minus 3 dx, plus the limit as m approaches 0 of m up to 2. So here, the limit as n approaches 0 from the left, integral of x to the minus 3.
Negative 1, 4, x. Oh, negative 1/2.
Negative x negative.
Negative 1/2 x and negative 2 between n and 2. So this would become the limit as n approaches 0 of, and plug in the n, this is minus 1 over 2n squared, plus if I plug in minus 1, that's just a half, plus limit as n 2 minus 1 over 8 plus plug in the m. And obviously this guy here diverges, right, that goes to negative infinity. And so this guy diverges. And finally, E. Okay, ideas on that guy?
Well, you got two bad points.
There are two bad points, which are
0 and
Zero.
infinity.
both the 0 and infinity. Technically here, -1 is also a bad point, but it's not on our interval, so we don't have to worry about it. But both 0 and infinity are bad points here. So I would break this up, say from 0 to 1. It actually doesn't matter what constant you pick, so you just pick something that's not too ugly looking. Plus from 1 to infinity. So this becomes a limit as n approaches 0 of n up to 1. Plus limit as m approaches infinity 1 up to n. So the moment the limits are going to hang out, I have to worry about the integration. How do you integrate something like that?
Partial fractions. See that?
Would not be partial fractions. Why?
Instead of the whole polynomial.
Because it's not a polynomial. The radical messes that up. Okay, so partial fractions only for rational functions, ratio of polynomials.
You substitute, u squared for x, and then is it gonna be like tangent inverse?
Yeah, so trick here is we're on a positive interval, so the x here is literally just the radical of x squared. And so I'd kind of let that be your u. So what I could do is u squared equals x. So that would get me a u squared plus 1, and then this would be my du. 2u du equals x, equals dx. And so this also means that u is equal to the radical of x, and you go everywhere and you plug that in. Let's say x is equal to n to 1. So my dx I can replace with 2u du. My radical x in the denominator I can replace with u. And this guy here I can replace with u squared plus 1. The u's cancel. And so I really have the integral of 1 over u squared plus 1 du. And the integral of that is the arctangent. And so that's arctangent of u, but u was radical x, so this is just tan inverse of the square root of x. I could only focus on 1/2 because it's literally the same integral, so I can just skip all the way down here. That's plus n goes to infinity of tan inverse of radical x of 1.
Did we lose a 2 there?
Did we lose a 2?
Yeah, where'd you put 2 go?
Oh, we did 2 here. So, 2, yeah. So now we just have the limit as n approaches 0 of 2 tan inverse, plug in 1, tan inverse of 1, minus 2 tan inverse of n plus limit as n is going to infinity of 2 tan inverse of radical n minus 2 tan inverse of 1. Okay, what's tan inverse of 1? It's pi over 4 times 2, so that this whole thing becomes pi over 2. Now, my n is approaching 0. What's tan inverse of 0? 0. Now, if my m is approaching infinity, what's the limit? Tan inverse of infinity.
Pi over 2.
That's also pi over 2 times 2 minus tan inverse of 1 is again pi over 2. So times tan inverse of 1 pi over 4 times 2, so it's pi over 2. So I end up with pi converges. As you can see, improper integrals it's really combining a lot of things that we would have seen before. We're combining everything we know from limits, all the things we know from integrals, kind of coming together in one problem to deal with having crazy limits. On Friday we'll move on to Arclength. I think in a little bit of time we have left, I can just kind of set it up for you so that on Friday we can just jump into some examples.
I have a question.
Oh, yes.
So then, what was the point of the comparison theorem?
That's when you don't know how to do the integral, so you compare it to another integral that you know how to do. So the comparison theorem means you're comparing one integral to another one to figure out the answer. There are a lot of problems like that in your homework where you're going to use that. There's probably like one problem on the test where you might have to use that. So Arclength refers to finding the length of an arbitrary curve. So I have some curve doing its thing over here from say x equals a to x equals b, and I want to find what is the length of this curve. Between a and b. do you know about length? Do you know, what kind of lengths do you remember? Do you know how to find it? I guess from high school.
Like the arc of a circle. Exactly.
Sure, but something even simpler, where you have a nice formula for it.
Line.
It's like a straight line. That's literally the easiest one, right? If it was just a straight line to here, you know how to find the formula for that. So the idea is, because we now are in calculus and we have the power of things like finding infinitesimal distances and taking Riemann sums to add them all up, the idea here is that we use a bunch of little straight lines to approximate the length of the curve. And the idea is, we come up with a formula to find the length of each of these lines, which we know from high school geometry. And then what we do is, we integrate over the curve. We add up all these straight lines. Integration is really a way of adding up a lot of things, an infinite number of things. So the idea is, we dissect this into subintervals. On each interval, we construct a line. We find the length of that line using our old geometry formula, and then use integration to say we're cutting up into an infinite number of pieces, so eventually all these lines are super close to the curve, and that's the idea. And so basically, if you take the length of one subline, roughly speaking, what the formula told you was what? It was the square root of x2 minus x1 squared plus y2 minus y1 squared, right? You apply Pythagoras' theorem to figure that out. But what you can think of that is, it's a change in x and the change in y, right? That's really what you were doing, right? And what you can do here, these are positive numbers, I can sort of factor out a change in x squared. So here I would have change in y over change in x squared. So I end up with this guy, 1 plus dy over dx squared, delta y over delta x squared, delta x. It turns out that so if you want to find the total length, now I'm being very hand-wavy here, but this is the basic idea. You compute it as a Riemann sum, so you integrate from a to b. Your delta x, when you throw it in a Riemann sum, becomes your dx. Remember that? And so we end up having the square root 1 plus, what does delta y over delta x become? When we throw calculus on top of it, it's the slope. It's basically y prime, or dy dx. Right? So the idea is you're letting the delta x, the lengths of these subintervals, go to 0, and that's definition of the derivative, right? The limit of the difference quotient as the denominator goes to 0. And so we basically end up with this formula. And so that guy, so once you start slapping calculus on all of these guys, you can replace this by this. And so it turns out, provided we can actually find the derivative at every point along this curve that we care about, we can actually find the length of the curve using calculus. It ends up being an integral. Suppose y equals f of x is a differentiable function. On the interval ab, then the length of f of x from x equals a to x equals b is given by this formula. and this is called the Arclength formula. So this is kind of the outline of the proof. Yet, of course, an actual proof would get a lot more specific and technical than this, but this is basically the gist of the idea. We kind of break it up into smaller little lines, and we can come up with a point, right? Which is literally what calculus is about. The whole point of calculus is approximating things using straight lines. That's kind of what we need to do. Yeah.
So what we're doing is taking dy over dx at each point on the curve, right?
Huh?
Like, we're taking dy over dx at each point on the curve?
On each subinterval, yeah, you're finding the slope of all these
Okay.
lines.
Okay.
Right. So you have to be able to do it everywhere. So it makes
Oh,
sense
okay.
when you plug it
So
into this form.
the integral breaks up into infinite amount of little lines.
Yeah,
Okay.
an infinite amount of subintervals, the same guys from your Riemann subs. So we'll stop there. We'll actually use this form to compute a bunch of lengths on Friday.
Is that work due
Maybe we
Friday?
won't work. What?
Is that work due Friday?
For improper integrals.